no longer active in the cell. And when that happens, then your cell can no longer keep dividing. So this is looking at enzymatic activity, but you would notice that growth would parallel this. Because when the enzymes start to unfold, the bacteria can no longer feed itself and undergo metabolism, right? That it needs to stay alive. If this was a bacterium that lived in the hot springs in Yellowstone, it's one of those cool archaea, then this would be shifted way over here, right? Because its enzymes would be designed to work at really high temperatures. So depending on the optimal temperature for an organism, its enzymes are going to have evolved to work at those temperatures too. All right, so this is a denatured protein. What happens to the enzyme over here? Is it unfolding? No, it's just cooler, right? So the reaction is happening at a slower rate. Right? You can freeze thaw enzymes a bunch of times and potentially denature some of them, but generally freezing is okay and won't hurt them. In fact, when you work with enzymes on the lab bench, we put them in ice usually to protect them. But if you heat them, you will kill them. You will kill the enzymatic activity. Okay. Another thing that we have to worry about, and again, we talked about this with respect to bacterial growth, and so we're having the same conversation, but talking more specifically about the effect. Why does pH, why does temperature have an effect on bacterial growth? So enzymes are also affected by pH. So here's our pH scale, 0 really acidic, 10 really basic. Around pH 7 or so, we tend to think 7.4 is your blood. Bacteria are really happy after about pH 4.6 or so. And so you can see our enzymatic activity in this particular case peaks at a little bit over 4. And so in different enzymes, you have enzymes in your stomach that are active at pH 2, and you have enzymes in your blood that are active lower, or active at higher pHs. So it depends on what the job of the enzyme is. What happens below pH 0 and above pH 10 is actually the same in this case. When you change pH, you're changing hydrogen ion concentrations, H pluses, and OH hydroxide ion concentrations, OH minuses, right? When you have a high H plus concentration, what it's going to do is it's going to bind to all of the negative charges on this protein and disrupt any ionic interactions, potentially any hydrogen bonding as well. And the same thing happens when the OH minus concentration is high. It's going to bind to any positively charged amino acids. And again, that's going to weaken the interactions between the protein chains and cause it to start to unfold. So you can denature proteins with too much acid, and you can denature proteins with too much base. Okay? So both high temperature will kill bacteria, but actually too much acid or too much base can also kill bacteria. And so we're looking at the effect there of pH. And of course, if it's damaging the enzymes, the bacteria can't survive without the enzymes. So, we can look at this with respect to bacterial growth, and it's going to parallel that of the enzymes. Okay, let's do a clicker question here. So both C and D is correct? Okay. If you missed that, does it make sense now? Increases in temperature increase the rate of chemical reactions because orientation of the collision, that's going to be random. So actually, you guys did really well on this compared to prior classes. Except for the people who said C, I guess. All right, I take that back. But the answer is B, there are more collisions, right? So the higher the temperature, the more kinetic energy, the more bouncing and more collisions are going to happen. But the orientation is going to be, the orientation is a random thing without an enzyme. It doesn't actually say in the absence of an enzyme, which I should have added. Yes?
But because there's more collisions, wouldn't that raise the percentage of the chances that they would be in the correct?
So if 50% of the collisions are in the right orientation, and I raise the temperature 10 degrees, I'm going to have twice as many collisions, but twice as many will also be in the wrong orientation, and twice as many will be in the right orientation, so the percentage overall is going to be the same? Yeah. Okay. But this is a poorly worded question, because I should have added in the absence of an enzyme. Yes? Because if you thought that this was in the presence of an enzyme, you might actually have picked A. So if you picked A for that reason, then that was my fault and not your fault. Yes? So just to point that out, yes.
And would that mean that if in the presence of the enzyme and with the increase of temperature, you're giving enough energy and you're having the enzyme putting the reactants into the right?
Yeah, so in the presence of an enzyme, this gets really complicated. Because in the presence of an enzyme, all of the reactants will be in the correct orientation. But if the temperature goes too high, you could denature your enzyme and have no reaction at all. So this gets to be a really messy question in the presence of an enzyme.
Oh,
Does that make sense what I just said?
okay.
Yeah, so it will be 100% will be in the correct orientation, but once the enzyme gets too hot, it's going to fall apart, and then you won't have any reaction at all. Okay. So not a good question to put on an exam because it's so poorly written, but fun to talk about afterwards as a clicker question. All right, here's another one. All right, last chance to click in. All right, so most of you saying B, or just saying E, and I agree. So it won't break the covalent bonds because typically those are the peptide bonds. There are some disulfide bridges, but those won't be broken by a change, just a change in pH or a change in temperature. But a change in pH and temperature could disrupt hydrogen bonds, and certainly a temperature change could disrupt hydrophobic interactions. Changing the pH could absolutely change the charges of acidic or basic amino acids. So this answer, the best answer is B, C, or D for this one. Okay? So A would be the only answer that wasn't partially correct, if not fully correct. All right. So let's move on and talk a little bit about the inhibitors of enzymes. And we wanted to understand two kinds of inhibitors. These get actually really important to understand how some antibiotics work. Another reason they're really important is because we want to understand, so I lost my train of thought. Antibiotics work and also how chemical reactions in cells are regulated. So we're going to talk about both competitive inhibition and non-competitive inhibition. And move on to this texty slide and look at a picture. All right, so a competitive inhibition is when the inhibitor binds to the active site. So here's our enzyme, here's our substrate. You can see it's happily fitting in there until, whoops, competition, right? A competitor literally, when it's a competitive inhibition, it literally gets in the way of the substrate binding to the active site. Pretty straightforward. It's competing for the same space. Yeah? So that's competitive inhibition. And here's an example of how an antibiotic that works by competitive inhibition. So you guys have heard of sulfa antibiotics? Real common one that people develop allergies to, but they're excellent for urinary tract infections in particular. So sulfanilamide looks a lot like a molecule called para-aminobenzoic acid. And para-aminobenzoic acid is something that bacteria need to synthesize folic acid. So you get folic acid as a vitamin if you eat just a regular healthy diet. Folic acid is actually one of the only vitamins where there is some evidence if you're pregnant or going to become pregnant. It's good to take folic acid. It reduces the rates of spina bifida, the spinal cord disease probably. But by the time you know you're pregnant, it's probably too late for the folic acid to help. So you basically have to, in childbearing years, take some extra folic acid, or if you're trying to get pregnant, you take it. Otherwise, taking it after the fact is not that helpful. But anyway. So folic acid is a really important molecule. It's used in DNA, building the building blocks for DNA, so making nucleotides. And bacteria don't actually, they make their own folic acid, and they need to be able to start with para-aminobenzoic acid to make the folic acid. So when you take a sulfanilamide, one of these sulfa drugs, what this does is it competes with the para-aminobenzoic acid and prevents the synthesis of folic acid. I don't know why it's so noisy out there. Do these molecules look similar? You can kind of imagine this molecule fitting into the same active site that this does and clogging it up and competing. Okay. So over the years, I've tried to find a better picture, and I have never found one. But anyway, this is the best I can kind of show you how this works. So here's para-aminobenzoic acid, and normally it binds to the pteridine, and then you add glutamic acid, and you can make folic acid. Here's the sulfonamide, and the sulfonamide will bind to the pteridine, but it binds irreversibly, and it prevents the second reaction. Yeah? So basically gums up the enzymatic pathway. It prevents the bacteria from continuing to make nucleic acids. They can't make new bacteria without new nucleic acids, and your bladder infection gets better. Yay! Okay, so that's a competitive inhibition in sort of a real-world scenario. All right, another interesting mechanism is non-competitive inhibition, and this one ends up being, in some ways, even more interesting to talk about because bacteria use this as a mechanism to regulate their growth and their activity. In non-competitive inhibition, this is the active site, but the non-competitive inhibitor binds to some other region of the enzyme. But when it binds there, it changes the active site structure so that this no longer binds. So the non-competitive inhibitor binds somewhere else, but when it does that, it changes the three-dimensional shape of the enzyme so that the substrate can no longer fit in here. This is called, this non-competitive inhibitor binds to something called an allosteric site. So it's not the active site, it's binding to an allosteric site. So that's the terminology that's used. Turns out that cyanide, you've heard of cyanide, right? Is a non-competitive inhibitor of the enzyme cytochrome C oxidase, which is part of the electron transport chain. So you've heard of cyanide messing up cellular respiration, I hope. So basically it prevents your cells from being able to make ATP from your electron transport chain. And that's very lethal, very fast. Not pleasant lethal, but fairly rapid. It binds irreversibly, which means that once it's on those enzymes, it's hard to get off. All right, let's talk for a little bit about using non-competitive inhibition to control a metabolic pathway. If you've taken physiology, you've probably talked about feedback loops and feedback inhibition. Okay, and this is essentially how this process works, except when we're talking about it at the enzymatic level. So here's our substrate, and here's our enzyme. And I want you to think for a minute. Now, a lot of you are familiar with glycolysis. We haven't talked about it yet, but you probably learned about it anywhere from high school biology up through other college biology classes. And if you haven't, just for giving you a little background, let's say this is a glucose molecule, and this is our end product of glycolysis, which would be pyruvate. So far, so good? Although it's, yeah. All right, so here's our glucose molecule, and the glucose binds to the enzyme, and then the enzyme, there's actually multiple enzymes. I'm sorry, my battery is going. I need to get new battery. The enzyme, the first enzyme, and then a product is formed, and that binds to a second enzyme, and another product is formed, and that binds to a third enzyme. And anyway, you end up with either the end product, which would be pyruvate, or some intermediate product in the pathway. Now, if there's lots and lots of glucose, and the cell needs this molecule, right? If you're short on this molecule, the cell needs it, then it makes sense for this pathway to keep going and keep making this molecule. Let me get a stick, because this is...
What kind of batteries does it take?
I think they're AAA's, but don't worry about it. I'll steal them from the biology
Are you
stock.
sure I have them right here?
I'm good. Thank you, though. I can take your batteries. All right, so here's our glucose molecule, and it worked on by this enzyme and gets changed into, actually it goes in, you're showing the glucose going into the enzyme. The enzyme has a product. This product goes into the next step in the pathway. Then it goes to make another product, which goes into this step in the pathway, and this is the next product. How are we doing so far? All right, as long as this molecule is in short supply, it makes sense for this to keep happening, right? Let's say this is a hat factory. Here's the first step of a hat factory. Now we've made this is a hat. As long as people are buying my hats, I should keep making hats, right? The same idea. I wish I could tell you it was different, but there's like no difference. The same general rule. Okay. Now let's say that I start to build up a lot of this end product. I've got a lot of hats and they're not selling. Should I keep making more hats?
No.
I got to figure out some way to not make hats. So in my hat factory, I look and say, geez, I got a lot of hats, I'm going to stop. But the cell doesn't, they don't have eyeballs, right? So it's got to figure out a way to sense how much end product it has. And what this does is what it does is it goes back and it binds. Remember our first enzyme here? See how it's got a little allosteric site that fits our hat? Fits right in here. And so when I start to build up my end product, it binds to this enzyme. And when it binds, it changes the active site so that our glucose no longer fits in. And it shuts down the pathway. Is that nifty or what? And that's really important because is this free or is this costing the cell energy? It's not free. It's costing the cell energy. Now, in glycolysis, ultimately the cell's going to get more energy from it at the end. But the fact is that breaking down glucose, if you're not going to use the glucose, you're better off turning it into glycogen or converting it to triglycerides rather than breaking it all the way down. So it makes a lot of sense for cells to shut down pathways that it doesn't need. Okay? So this is a feedback inhibition, right? And it's a mechanism of metabolic control. How are we doing on this? Yeah? My people in the back? All right. Answer a couple questions here. You want to know how many years Bill Cosby was sentenced to? Yeah. 10 years. Not enough. That's what I'm hearing. I'm just repeating what I'm hearing people say.
It'll be lost. Yep.
All right. Sorry, I distracted you with Bill Cosby. All right, last chance to sit again.
Yes.
All right, let's see what you guys said. A competitive inhibitor. So this is nice, 90%. Nice job. All right, let's see. Here's another one. The type of enzyme inhibitor that regulates metabolic pathways, turns them off is called? All right, so again, more than half of you getting this correct. Let's go through this though. So the type of enzyme inhibitor, if it's an inhibitor and it's functioning in a feedback loop, so regulating the metabolic pathway, then it's going to be a non-competitive inhibitor. Okay? And the non-competitive inhibitor is frequently the product of the metabolic pathway or some intermediate in that metabolic pathway. So both B and C, okay, makes sense. All right. All right, so here's a study guide question, really just kind of another way to ask the same question. There's really a limited number of questions I can come up with. I try to think of different ways to ask the same thing. So this is in study guide format. What is the difference between a competitive inhibitor and a non-competitive inhibitor? How do cells use non-competitive inhibition to regulate a metabolic pathway? So here there's two questions, right? So just reminding you that whenever you see a short answer or an essay question, you want to make sure you answer all the questions. And I did see this on the last exam where I had people answering just parts of it. And when you're nervous on an exam, because they're very stressful, it's really easy to miss something. So sometimes taking your pencil and underlining, breaking it down and underlining the different parts of the question so that you make sure you address them is helpful. So the first part says, what is the difference between a competitive inhibitor and a non-competitive inhibitor? And you could simply talk about where they bind to the enzyme, right? A competitive inhibitor binds to the active site, and a non-competitive inhibitor binds to the allosteric site, exactly right. And then you would talk about non-competitive inhibition to regulate metabolic pathways. You know, you could use my hat analogy or some other factor analogy. That enzymes are basically, they're assembly lines, right? Producing molecules that the cell needs. And when you get a buildup of a molecule and you have enough of it, the cell can use that molecule to then shut down the pathway at the beginning. Okay? And so you could draw your picture of an enzyme and show how that works. Okay. The next thing, I'm just going to look at some here. How am I? Okay, ATP. All right, so I got a few more slides and then we'll talk about chicken pox here. So how many of you love learning about oxidation reduction reactions in chemistry? Woo-hoo. In biology, they end up being a little bit simpler. So the way, what an oxidation reduction reaction refers to is reactions where one molecule loses electrons and another gains them. And in chemistry, it can be really hard to figure out sometimes which molecule got the electrons and which one gave them up. But the good news is in biology it's easy, because electrons in biology always go with hydrogen. And so you can almost always figure out who's been oxidized and who's been reduced by looking to see who's got more hydrogens. That's easy, right? Figure that the electrons are always going to travel with hydrogen. All right. So these redox reactions are really referred to, because I don't want you to go down to the chemistry department and get me in trouble. But I say my biology teacher said, I said in biology reactions, I said. The electrons are usually lost or gained with the hydrogen. So when we think about it with respect to glycolysis and Krebs and electron transport, we're usually pretty safe tracking hydrogen. But this is a traditional oxidation reduction reaction, so A here is going to be oxidized because it's losing electrons, right? But those electrons have to go somewhere. So if something is being oxidized, something else has to be reduced. Because electrons don't just poof disappear, right? They have to go somewhere in the universe. And so they're going on to the molecule being reduced. Why do we care about this in biology? Well, let me show you why. We care about this because it turns out that reduced molecules have lots of energy, and the oxidized molecules have very little energy. So gasoline is a hydrocarbon. It's a molecule full of carbons and hydrogens. And we put gasoline in our car, right? Unless you have an electric car. Someday I won't be able to use this analogy anymore. But you put gasoline in the car, and what comes out of your tailpipe is hopefully mostly carbon dioxide and water. So this is low energy and this is high energy. Can you put CO2 in your tailpipe and get your car to run? No, because there's very little energy in CO2. Okay, basically that's carbon stripped of most of its useful energy. All right, so this is actually not gasoline though. This is what molecule? the here's some people whispering. That's a triglyceride, you're right. Triglyceride. Okay, so this is a fat molecule. We use these molecules to store energy. Here's our 3 carbons, and here's the 3 fatty acid chains. For those of you who had nutrition, how many calories per gram do you get out of a fat molecule? 9, right? This is a carbohydrate molecule. It's our friend glucose. Do you see that it also has carbons and hydrogens? Okay, but and some of the carbons even have hydrogens on them, but we also have some oxygens and some OH groups. So this carbon, instead of having 3 hydrogens around it, it's really got 1, right? How many calories per gram in this molecule? 4. So this molecule has twice as much energy as this molecule? Yeah, it does, right? And proteins also have about 4 calories per gram. And then here's our carbon dioxide and water, and they're just useless in terms of energy. They're waste, right? So very energy poor. So we care about energy, oxidation, and reduction in biochemistry because we take, in the process of cells getting energy from molecules, cells take highly reduced molecules or moderately reduced molecules, and we oxidize them all the way down to CO2 and water. That's where the energy comes from. It comes from starting with a reduced molecule and creating more highly oxidized molecules. Here's an example of an oxidation reduction in biology. So here's lactate, and you can see that lactate has, let's kind of look at it here. So lactate's got a hydrogen, this is the same here, right? But you see there's more hydrogens on the second carbon, right? And then the CH3 thing. So this molecule, when you go from lactate to pyruvate, lactate is being oxidized because it's losing hydrogen. Except for if your chemistry teacher asks, we're going to say it's losing electrons. They went with the hydrogen, so we're safe, okay? So here's this molecule, lactate here is being oxidized, which means the pyruvate is being, actually in this case, pyruvate is the product, and then NAD plus is gaining those electrons in the form of hydrogen, it's being reduced. So our lactate is being oxidized and NAD plus is being reduced. So it's an oxidation reduction reaction in biology. And the enzyme that makes this happen is called lactate dehydrogenase. Okay? So it's removing a hydrogen from lactate. All right, so we care about this because reduced molecules have more energy. We just talked about this, but take a look at it again. Which molecule is more reduced, pyruvate or lactic acid? Last chances to click in. Oh. All right, I would do my experiment again, but I actually am running out of time, so I won't. So when we look, molecules that are more reduced have more what, Adam? More hydrogen. So which molecule has more hydrogens? Lactate. A lot of you said pyruvate. So if you saw it said pyruvate, I want you to look at each carbon. Because I'm going to give you some of these on the test, potentially even on the quiz on Thursday. So this carbon looks the same, right? But you see in this carbon there's a difference? Which one has more hydrogen? So this is more reduced because it's got more hydrogens? And this carbon's the same? If you missed this, will you ace it on the quiz on Thursday? Yes. Okay, all right. And if you don't think you're going to ace it on the quiz and you could come see me right after class, we could go over it again so that you feel really confident. All right, we're going to start with this slide next time, and so that we don't run out of time, I want to talk about chicken pox. Take a detour now. I hope we don't run out of time. All right, chicken pox, one of my least favorite viruses, or most favorite. I guess I think it's super interesting. Chickenpox is caused by the varicella zoster virus. Varicella zoster, varicella is a herpes virus. So it's in the herpes family. Like with herpes 1 and 2, with herpes simplex, it's just a different kind of herpes virus. And like herpes viruses, herpes is forever. When I was in high school, It was the early 80s, and people hadn't really heard of HIV yet. So the thing that we were all like scared into not trying to be, abstinence, they try to scare you into abstinence in high school, which we know totally doesn't work, but they did it anyway, is they would talk about herpes. Herpes is forever, right? And then HIV came along, and then everybody was afraid of dying from HIV because we could see people dying from it. But until then, we were afraid of herpes. Anyway, but chickenpox is also a herpes virus. And again, this was like measles. It was a childhood rite of passage. Everybody got the chickenpox. So in the early 1990s, before the chickenpox vaccine came out, 4 million people got varicella chickenpox. 8 to 18,000 were hospitalized, and 150 died every year. So you don't think of people dying from the chickenpox. But it's actually mostly pretty benign, but a fairly serious illness. When I was a little kid, kids would get the chickenpox, they'd be out for a week, and then they'd come back to school with the little dried scabs all over them. When I was little, I have 2 brothers. My mom tried really hard to get us the chickenpox, because that was what you did. One of the neighbor's kids got chickenpox, and you sent your kids over there to hang out with them, so that they would get the chickenpox too, and then your kids would get the chickenpox all at the same time, you'd get it over with. And we stubbornly did not get the chickenpox, not because she didn't try. And so I got into college, and at some point my mom figured that we'd had the chickenpox and we just had a mild case, and she didn't know. And then while my first year of college, while I was incredibly immature and homesick and wanted to be home every weekend, my younger brother got the chickenpox, and my mom said, "Don't come home." So I'm in tears, I need to come home. Don't come home, your brother has chickenpox. And so then I figured the next weekend I'd live a whole another week. The next weekend my other brother got the chickenpox. And I still couldn't come home. The problem though, after the trauma of just being trapped for 2 more weeks at college, was that I actually did not have chickenpox. And these people who get hospitalized and get really sick tend to be people who are older. It's when you get really sick. And so in 1995, when the vaccine became available, I had finished graduate school and moved up here. And the minute I heard about that vaccine, man, I marched my high knee into a pediatrician's office and I said, I need that vaccine. I have never had a chickenpox. And the only place you could get them was a pediatrician's office. And they sat me down in a chair that was this tall. And they put a pink Cinderella banner on my arm. And